This is the second part of a three-part series on the X-ray circuit. This video is looking at the secondary circuit, also known as the high voltage section. The entire X-ray circuit looks like this, but today we'll talk about this area here. This area of the X-ray circuit is the secondary circuit or high voltage circuit. First, we'll discuss this step-up transformer. A step-up transformer on our X-ray circuit takes voltage from the variable turn ratio autotransformer and increases those volts to kilovolts. This increase in amplitude takes us from 100 to 400 volts to around 25 to 150 kilovolts. However, we don't want 25 to 150 kilovolts of alternating current to go into our X-ray tube. We need direct current. So how do we turn AC into DC? We use something called a rectifier, as seen here. A rectifier converts alternating current into direct current. This is important to us because we need one side of the X-ray tube to be negatively charged and the other side to be positively charged. If we used an alternating current on the X-ray tube, then electrons from the anode would go to the cathode and cause all sorts of havoc. The electrons must go from cathode to anode for us to produce radiation. To understand rectifiers, we need to look at diodes. These diodes act as one-way signs for the current. They allow electrons to flow in one direction only. We have two rules when working with diodes and rectifiers. The first rule is that electrons always flow from negative to positive. Electrons are optimistic. They want to go from a negative space to a positive space. The second rule is electrons always flow in the opposite direction of the arrows on the diode symbol. These symbols were written for electrical engineers who think of current as positive charges moving along. But we as physicists and as radiographic technologists know current is negatively charged and go from negative to positive. Thus, electrons always flow in the opposite direction of the arrows on the diode symbol. Let's put our two rules to the test. First, electrons flow from the negative side to the positive side. Next, the electrons will encounter their first diode. Will the electrons go through? Yes, because electrons always flow in the opposite direction of the arrows on the diode symbol. The electrons continue along and reach the second diode. Will the electrons go through this second diode? Yes, because again, electrons always flow in the opposite direction of the arrows on the diode symbol. Let's try again, but flip the diodes. All right, so first, electrons will flow from the negative side to the positive side. Then the electrons will counter their first diode. Will the electrons go through? No, because electrons only flow in the opposite direction of the arrows on the diode symbol. Because the diode is pointing in the same direction as the current flows, no electrons will go through. There are two types of rectifiers, a half-wave rectifier and a full-wave rectifier. What's that mean, half-wave and full-wave, and what's the difference? A half-wave rectifier only uses half of the available current. Here's a graph of a 60 Hz alternating current system. Each cycle is 1/60th of a second, so there are 60 cycles in 1 second. The yellow indicates the first half of the cycle, which is 1/120th of a second. The yellow here indicates the last half of the cycle. This too is 1/120th of a second. Alternating currents flip the polarity of our step-up transformer. So during one half of the cycle, the polarity looks like this. Then on the other half of the cycle, polarity flips and looks like this. The top half of the graph indicates one half of the polarity cycle, and the bottom half indicates the other half of the polarity cycle. Every 1/120th of a second, the polarity flips, and so does the line graph. Let's combine our two rules with this line graph. First, electrons will flow from the negative side to the positive side. Then the electrons will encounter the first diode. Will the electrons go through? Yes, because electrons always flow in the opposite direction of the arrows on the diode symbol. The electrons continue along and reach the second diode. Again, will the electrons go through? Yes, because the electrons always flow in the opposite direction of the arrows on the diode symbol. Because electrons completed their journey from negative to positive, it is represented on the graph like this. Next, we'll look at the second half of the cycle and flip the polarity. First, electrons will flow from the negative side to the positive side. Then the electrons will encounter the first diode. Will the electrons go through? No, because electrons always flow in the opposite direction of the arrows on the diode symbol. Because electrons did not complete their journey from negative to positive, it is represented on the graph as a flat line. Altogether, the graph of a half-wave rectifier looks like this. Notice that the graph is only using half of the full wave. This is because only half of the electrons provided are being used. If our X-ray machine is only using half of the electrons provided to it, then our techniques are only half as strong as it would be if all electrons were used. The other type of rectifier is the full wave rectifier. The full wave rectifier uses all electrons. And how is this possible? We can demonstrate that by using the rectifier rules. First, we go from negative to positive. Then the electrons have a choice. Will they go up to this diode or down to this diode? Which will they choose? They go down because that diode will let them through. The electrons then travel to the next split. Will they continue going straight up or veer off to the side? They'll go to the side because this diode would block them from continuing. Now the electrons can travel across the tube and onto the other side. At the next break, we have a tough decision, which way to go. If the electrons travel down, they would be able to go through this diode. However, remember the first rule, electrons go from negative to positive. If they took the path traveling down, they'd be going from negative to negative. So the electrons will travel up. At the last intersection, the electrons make one last decision. If they go down, they'll be going toward the negative side. So instead, they finish their journey to the positive side. Whew, all that traveling for only 1/2 of the cycle. That's a lot to do in 1/120th of a second. To complete the cycle, we must flip the poles. First, we go from negative to positive, and then the electrons will have a choice. They can go up through this diode or down through this diode. So which do they choose? They go down because that diode will let them through. The electrons then travel to the next split. Will they continue going down or veer off to the side? They'll go to the side because this diode would block them from continuing. Now the electrons can travel across the X-ray tube and onto the other side. At the next intersection, if the electrons traveled up, they'd be able to go through this diode. However, remember the first rule, electrons go from negative to positive. If they took this path, traveling up, they'd be going from negative to negative, so the electrons travel down. At the last intersection, the electrons can make one last decision. If they go down, they'd be going back toward the negative side, so instead, they finish their journey to the positive side. Because electrons completed their journey from negative to positive, it's represented on the graph like this. And because electrons completed their journey from negative to positive when we flip the polarity, it's also represented on the graph like this. Altogether, the graph of a full wave rectifier looks like this. Now our X-ray machines are using all of the electrons. We often demonstrate current flow like this. The half-wave rectifier only uses half of the electrons provided to it. The full-wave rectifier uses all of the electrons provided to it. Finally, we have the MA meter and its rectifier. The rectifier before the MA meter does the exact same thing as the rectifier before the X-ray tube. It's just drawn differently. So this and this do the exact same thing. They convert AC to DC. The MA meter tells us what MA we're actually using. Follow along as the electrons travel through this circuit during one half of the polarity cycle. Then let's flip the polarity, and one more time, follow as the electrons travel through this circuit.